Hello everyone, my name is Saina Sanni and this is a joint work with Emmanuel Filio, Ismail Jekkar and Kushraj Madanani. So finite state transducer are machines that reads an input word and produces an output word using finite memory. So while automata accept a set of words, transducers extend automata by also producing output along each transitions. So the red color indicates the output word. So there is an underlying automata, and for each word accepted by the automaton, it also produces an output obtained by concatenating the output produced along the run of the input word. So in this example, this transducer output letters at odd positions. And transducers can be seen as defining a relation between input and output words. And such relations are called rational relations. And this is another example of a rational relation, which is a set of all pairs of words UV, where V is a subword of U. Now, functions defined by transducers are called rational functions, where for each input word accepted, there is exactly one output word produced. An example is this function f last, which reads a word of the form u sigma, where u is a word and sigma is the last letter, and produces an output after moving the last letter to the front, that is sigma u. So see how this transducer works. You start from an initial state. At this point, you don't know what the last letter is going to be. So you make a guess here. You go right, assuming that the last letter is going to be A, and output A at the front. And you accept this path only if the last letter is A. Similarly, you go left, assuming that the last letter is B, and output accordingly. You can see that this transducer is not deterministic in the input, even though it defines a function. Now, in fact, functions defined by input deterministic transducers are called sequential functions. In the previous example, the function f last is not sequential, since intuitively guessing the last letter was actually necessary. So a quick recap, sequential functions are a strict subset of rational functions, which are a strict subset of rational relations. Now I recall the class membership problems, which are functionality and determinization. So in functionality, you are given a rational relation and you ask, is it a function? That is, for each input word, there is exactly one output word. And in determinization, you are given a rational function and you ask, is it sequential? That is, does there exist an input deterministic transducer that defines this function? And both are well studied in the literature and shown to be decidable in polynomial time. Now we study the approximate versions of these problems, which are approximate functionality and approximate determinization. So in approximate functionality, you are given a rational relation and you ask, is it close to a function? Instead of exactly equal to a function, is it close? Okay. And in approximate determinization, you ask if the given rational function is close to a sequential function. And this closeness can be measured using a notion of distance between functions or relations. And we are interested in edit distances. So edit distance between two words is the minimum number of edits required to rewrite one word to another. Some example of edits are like substituting a letter with another, inserting or deleting a letter. For example, if you are allowed all these edit operations, the edit distance between the word hello and hello is 2. Substitute H with Y and insert a W at the end. Now there are different types of edit distances based on the allowed edit operations, such as Levenstein is the one where you are allowed insertion, deletion and substitution, while Hamming allows only substitutions. Now using this notion of distance between words, we can lift it to distance between functions as follows. Let D be a distance on words. Okay, the distance between functions f and g is defined as, if the domains are not the same, then distance is infinity. And if the domains are the same, then for each input word w in their domains, you compute the distance between the output of f and g on w. And you do that for all such w in their domains and take the supremum. So the distance between two functions is the least upper bound of the distance between their respective outputs on all inputs. For example, consider the function f last, which moves the last letter up front, and the identity function that outputs exactly the same word as input. Now what is their distance, say with respect to Levenstein, where you are allowed insertion, deletion and substitution? So first of all, their domains are the same. Okay. Now for each input, the distance between their outputs with respect to Levenstein is at most 2. Delete the first sigma and insert a sigma at the end. And this is true for any arbitrary input word, and hence the distance is 2 with respect to Levenstein. However, in the case of Hamming, Since only substitutions are allowed, there are input instances where you may have to substitute each letter in the output to obtain the other output. And as the length of the word increases, the distance also increases, and when you take the supremum, their Hamming distance become infinity. So, so this is how we define the distance between two functions. And similarly, we can define distance between relations, and we say two functions or relations are close if their distance is finite. So it is also known that the edit distance between rational functions is computable. Now we formally define the approximate class membership problems. So in approximate functionality, you are given a rational relation and you ask, does there exist a rational function such that their distance is finite? Similarly, in approximate determinization, you are given a rational function and you ask, does there exist a sequential function such that their distance is finite? And our results are as follows. Both approximate functionality and approximate determinization are decidable with respect to Hamming and Levenshtein family of distances. So let me give you the characterization for approximate determinization with respect to Levenshtein. So in exact determinization, you ask, given a transducer, can you determinize it? While in approximate determinization, you ask, can you determinize it, but now you are allowed a few edits in the output. So as you have already seen, F last is not sequential. That is, it is not exactly determinizable. However, F last is approximately determinizable with respect to Levenshtein, since the anti-function is sequential and their distance is finite. Now, exact determinization is characterized using a structural property of transducer called twinning property, and we define something called approximate twinning property and strongly connected twinning property to characterize approximate determinization with respect to Levenshtein distances. We say a transducer satisfies approximate twinning if and only if for all synchronous runs on the same input. That is, here the inputs are the same, U and V are the same, okay, and outputs can be different. If for all synchronous runs on the same input, the output produced along the synchronous loops, that is V1 and V2, needs to be conjugate or cyclic shifts of each other. That is, there exist words x and y such that V1 can be written as xy and V2 can be written as yx. Why this conjugacy is important? Because in approximate determinization, you are allowed only finite number of edits in the output when you determinize it. So if the loops produce conjugate output words, that is of the form xy and yx, when you determinize it on seeing the input v, okay, you can choose to keep either of this output. Since even if the loop is pumped any number of times, the number of edits required between these outputs, that is xy, xy, xy and yx, 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 is 2 into length of x. You can delete the first x and insert a x at the end. And hence the distance remains finite even if you pump the loops any number of times. So ATP characterizes this notion of loops being conjugate. However, ATP is sufficient only for certain subclasses of rational function to be approximate determinizable, like union of input deterministic transducer or certain kind of concatenation of input deterministic transducers. Now, for rational functions to be approximately determinizable with respect to Levenshtein, along with ATP, you also need a strongly connected twinning property. That is, the twinning property must hold within the strongly connected components of the transducer. Why this? Intuitively, you also require no edits within the strongly connected components of the transducers for the rational function to be approximately determinizable. Okay. So now both ATP and STP are shown to be decidable properties for transducers, and hence approximate determinization is decidable. So these are our results, and one of the future work is approximate synthesis or sequential uniformization. In exact synthesis, you are given a rational relation and you ask, does there exist a sequential uniformizer of R? While in approximate synthesis, you are given a rational relation and you ask, does there exist a sequential function that is close to some uniformizer of R? And a uniformizer of R is a function that is a subset of R and also have the same domain as that of R. Now this exact synthesis is known to be undecidable, and we prove that approximate synthesis is undecidable with respect to Levenshtein family of distances and is still open for Hamming distances. Thank you. Any questions?